So where we left off on Friday, we left off here talking about, let me go back to the beginning. We left off talking about pre-existing chiral centers and how to generate stereochemistry in a reaction. And one of the ways we said was, excuse me, to use a chiral catalyst. And the other way we talked about was to use a chiral start material or something that already has a chiral center built in. Right. So that's where we left off with this example right here. We talked about this epoxide example number 4 and how that tert-butyl group being on a chiral center near where the reaction would take place, it would control the outcome of the reaction, whether or not that epoxide will be on the opposite side of that group or on the same side. So we kind of use that to talk about major and minor and product distribution. And we talked about sterics, which is simply a physical interaction between substituents, right? If they're large enough to touch, that's going to create a steric interaction, and it's going to increase the energy of the reaction itself, as well as the product, right? When you make the product, one of those products is going to be a little higher in energy than the other one and a little bit less accessible. That's why you see the percentages, 90% for the product where the groups are on opposite sides, because that's the preferred orientation of those groups. And then 10% where the groups are on the same side, because that's the disfavored orientation for those groups. That's why you don't get as much. All right, so let's go to the next example, in number 2. And this is an example of a reaction that we call oxymercuration. And both of these reactions, hydroboration, oxidation, as well as oxymercuration, they both give you the same outcome, right? It's a way to convert, let me zoom in on that. Alkenes into alcohols, right? There's a difference in this reaction, though. And there's a word that we learned in part 1 dealing with this reaction. That describes the difference in the outcome, right? So first of all, I know I asked that that you would look this up over the weekend. I know it was a holiday, barbecue, and cold, whatever. But did anybody happen to look up the oxymercuration reaction? Can somebody tell me what the difference between that reaction and the reaction up top? What's the difference between those two? The difference is in what we call the regiochemistry. Right? This is basically the location. So if you have an alkene that's substituted like this, depending on which reaction you do, I'm not going to put the reagents, I'm just going to put the name. So you can do hydroboration, followed by oxidation, or you can do oxymercuration. right? The difference in these two reactions is the regiochemistry, or the location of the alcohol in the product, right? So if you do hydroboration oxidation, I'm going to show you the intermediate. So the intermediate is going to look like this, where the H here is added, and then there's a, right, because up here, the reagents, the first reagent is BH3, boron trihydride, right? So that is added across the double bond, right? Oh, sorry, wrong location. My bad. So that's an H here, and then the BH2 is here, right? And then in the oxidation step, that BH2 gets converted into an alcohol, right? And then the other reaction, and I know this is a review, but it's okay, we need it. The other reaction, there's an intermediate that looks like this, where your mercury is here, right? And then when you pop that open with water, which is the second reagent, you can see it right there, and then treat it with the sodium borohydride, you end up with this. Now, what's the difference in those two? What do you see?
The alcohol was added to a different side.
It's on a different side of the double bond, right? You had two carbons in that double bond where that alcohol could add. It could add here or here, right? This side is the most substituted side. And then this side over here will be the least substituted side, right? It has less carbons attached. Let me change the color of that. So least substituted. That's what we mean by regiochemistry for this particular reaction, right? The OH is either going to add to the more substituted side or to the least substituted side. So in this reaction, when it adds to the most substituted side, can somebody tell me what that's called? What type of addition that is? We learned it in part 1 on not just this reaction, but also when we took alkenes and added. Go ahead. When we add HX across alkenes, it's the same type of addition too. It's a specific word that we learn that describes when you add a nucleophile to the more substituted side of an alkene.
Markovnikov.
Who was that? You're right. This is the Markovnikov product. And then the BH3, hydroboration oxidation, that would be, go ahead. What would we call that? By adding OH to the least substituted side. It would be anti-Markovnikov. All right, all that information to go back up to this top problem and work it, and answer the question, right? So if you look at the alkene, any questions about that before we jump up here? All right. Thank you for that answer too. I couldn't see who it was, but I appreciate that. If you go back, we go back to here and look at the alkene. These are the two carbons in question. Which carbon is more substituted?
The one on the right.
Good, good. And we know that oxymercuration is going to follow Markovnikov's rule. Right? So even if you don't know the mechanism of this particular reaction, even if you don't know the mechanism, you can predict the product, because the outcome of the reaction is to take the alkene and convert it into an alcohol using Markovnikov addition, right? So what you're basically saying with this reaction and the top reaction is you're adding a hydrogen to one side and an OH to the other side. That's what these reactions do. Basically, it's like adding water to the alkene, but the location of the OH changes based on which set of reagents you use. So here, if I'm doing oxymercuration and this is my double bond, which carbon is going to have the OH added to it, and which carbon is going to have the H added to it? Again, the question is, which carbon is more substituted?
The right carbon is more substituted.
Carbon on the right, good. Right, so my product, I'm gonna go ahead and draw this out. So this is going to be one of my products. What is it? Oh, TMS. All right, so here, I'm just going to draw it like this with the OH here. All right. Is everybody in agreement that these are the carbons of that alkene, and that the carbon on the right is more substituted? So that's where my OH is going. Anybody disagree or not understand that?
What do you mean by more substituted?
So if you look at the carbons themselves, how many the alkene carbons? The carbon on the alkene carbon on the right has 2 carbons attached to it. You agree with that?
Yes.
And then the one on the left only has 1 carbon attached to it, because the other group is not shown, but the other group is a hydrogen right there.
Okay.
Mm-hmm. So the carbon that has the most carbon substituents bonded to it is more substituted.
Okay, gotcha.
Mm-hmm. Good question, by the way. I'll write that in. All right, so that's that. So now, what would the other product look like? Would it look like this? Yes, no, maybe. You're going to get both, right? Don't be scared. Speak up.
Does it not add to the other?
Say
Never
again.
mind. Never mind.
Do you see it? Like, you're going to get both of those products. One where the OH is on the same side of the pre-existing chiral center, which is right here. Let's not miss that. And one where it's on our opposite side. All right, so now somebody read the question. And let's say for the sake of argument that it is the ratio is 55 to 45. Because I don't want to say 50-50 because there is some influence, but it's not a lot. So let's say the ratio is 55 to 45 for the two products. All right. We've done A already. We've drawn the products. Why do you think the ratio goes down? Like, why do you think the difference in compared to the first problem? Why do you think it goes down? Think about that for a second. And while you're thinking about it, think about what factors affect that ratio, right? There are two things we said that affected the ratio of the product, the stereoisomers that you make in the product when you have a pre-existing chiral center. What were those two things that we said affected that?
Proximity.
Okay, good. What else?
Size.
Size and proximity. So if you look at the two reactions, tell me what changed. The size of the group is still the same, isn't it? If you compare the reaction that we did in number 1 to the reaction that we did in number 2, the size of the group didn't change. What changed?
The proximity.
Proximity. I agree with that. Why do you say that? Tell me why you say that.
It's on a different side, so it's like one of them is opposite sides of the big group, and the other one is on the same side as the big group.
Okay, but don't we have that in the top two? We got a group that's opposite and same up here as well, right? So when you think about proximity, that's location or closeness to that chiral center. So you're in the ballpark though, so I want you to keep pushing. Where is the hydroxyl group, the alcohol group, relative to that chiral center in the second reaction compared to the first? Think about it that way.
In the second reaction, it's sent towards the back.
Is it further away from that group, or is it closer? Look at the. Let me back up. Look at the reaction here, right? Here's the chiral center. Notice where the alcohol is. It's adjacent. It's on the carbon right next door. Am I right?
Yes.
Now compare that to this. Where is it here? This is the chiral center. It's not adjacent to it, is it?
No, it's further away.
Further away. That's what we mean when we talk about proximity. That reaction took place a little bit further away from the pre-existing chiral center in this case, right? Look at the effect. The ratio went from being 90 to 10 up here, I think, 80-20, my bad. Up here is 80-20. Now it's close to 50-50, right? It's 55 to 45. Why? We just said it, but I want to hear somebody else say it. That's not me. Why the ratio drop like that?
It's the substituents are farther apart. It can add on either side easier or almost the same.
Okay, good. You're right. So the fact that the pre-existing chiral center, that the reaction takes place further away from that, it has less influence. So that alcohol can add from the same side or opposite side with basically the same level of accessibility. That's good. You're right. So let's put that in a sentence, right? Because when it says explain, that needs to be in a sentence. It can't just be one word, proximity, or or size, right? It's got to be a sentence. So how we word that sentence? The ratio, I'll start you off, decreases because what?
The substituents are further apart.
Okay, so we'll
Or-
say that. Let's say the reactive site is further away from that pre-existing chiral center. Because that's how we couched this up when we first started talking about it. So the reactive site is further. Nah, that's not good. Right? The ratio decreases because the reactive site is further away from the chiral center. Right? That's why you see the drop to almost 50-50. And that's only one carbon difference, but that's when you're talking about working on a molecular level, that's far, right? That bond length, that carbon-carbon bond length, something like 153 picometers or something like that. So on a molecular level and on an atomic level, that's a pretty good distance. And you're talking about going from being right adjacent to that pre-existing chiral center to one carbon removed from it, right? So that changes everything. All right. Questions about this example? I know we went through the Amazon rainforest to get to it, but hopefully the introductory part made the other part make sense. All right. Any questions about that?
Yeah, I have a question.
Go right ahead.
I'm trying to put this into a sentence. So proximity
Okay.
and size, proximity and size are considered when determining what?
How a pre-existing chiral center affects the outcome of a reaction,
Okay.
right? Because that pre-existing chiral center means that your products are also going to be chiral.
Okay.
And
Thank you.
it's going to control how much of whatever diastereomer you get in the product, whatever two diastereomers you get is going to control how much of each one you get.
Okay.
Just by already being pre-existent and causing that bias. Remember we talked about the word bias when we first started talking about this. It causes a bias in the transition state of the reaction, and therefore you're going to have competing processes. And you're going to have two different products. One of them is going to be more favorable because of its orientation relative to the pre-existing chiral center. The other one will be less favorable. So in this case, there's really no difference between these two because the OH is further away. So it doesn't have the pre-existing chiral center doesn't have the same effect as it would here, where your OH groups are right next door to it. All right. Did that answer your question?
Yes, it did. Thank you.
Okay. All right, good. All right, let's look at the next question. All right. When the reaction number 2 is carried out with this start material, how would you expect the ratio of stereoisomers to change? Would you expect the major product to be increased? Right? How many of you remember this functional group from Organic 1? What that is?
Tert-butyl.
Tert-butyl group. Right? So if we were to write this out, let's see. So this is O silicon. You will have 3 of these on here. I know it looks like a chicken foot, but it's not. It's 3 carbons attached to a central carbon. It's a very large functional group, very large alkyl group. Right, so this is now my start material. What did I change compared to now? Let's go back to here. Notice these are all methyl groups, not tiny relative to a hydrogen, but definitely not the same size of a tert-butyl. So what did we change? Did we change the size, or did we change the proximity to the reactive sites?
Size.
Change the size. So somebody read that question and tell me how you would answer it. Anybody
I
but a
would say yes. Yes, the ratio of stereoisomers will change, and I would expect the major product to increase because it's going to be harder for the reaction to take place because it's blocking it.
It's a bigger group. Right, so the size of this group is going to actually change that. And that's what we expect, right? We expect that if that group is bigger, then it's going to have a little bit more influence over the product distribution, right? I want you to draw those 2 products, by the way. We don't have to do it right now. So this is on your own. Draw the 2 products. And then this doesn't have to be exact, but I want you to estimate the ratio between them. All right, so I want you to draw the 2 products you would get from that and then come up with a ratio. And determine which one is, of course, major and minor. Thank you, Russell. Major and minor. Right, so draw those 2 products and then you can estimate a ratio. There's no wrong answer there, but it can't be the same ratio as that we had in the problem number 2. It can't be that number. We already said that the ratio is going to change in favor of the major product. So, but the number is up to you. Any questions about that? All right. We're going to actually shift gears here and transition to the next topic. I think on the syllabus, the first test is slated for the 15th, I think. Is that right? September the 15th. So I'm gonna add in one more topic. And then we'll just take a test over those 2 topics. Stereochemistry, and then this topic, which is the synthesis of alkyl halides. Let me fix that, sorry. Right. From Organic 1, somebody tell me what the definition of an alkyl halide is. It's a type of functional group. Tell me what it is. Anybody?
A carbon bonded to a halide
Excellent.
or halogen.
That's exactly right. So let's just say if I have something like this, right, and I have a bromine here, right? This is an alkyl halide, right? The alkyl part is the chain, and of course the halide part is the halogen. Right, so you have an alkyl portion, you got a halogen portion. So we call that functional group an alkyl halide. Believe it or not, this is one of the most important functional groups in all of organic chemistry. And the reason is, well, let's talk about the reason. It's a very important functional group, right? The carbon bromine bond. Anybody, is that bond polarized at all? Or not? And by polarized, I said no. Okay. Anyone else?
Yes.
Okay, we got a coin flip. I wish I had a digital coin I could tap. So what causes a bond to be polarized? Anybody?
Different electronegativities.
The difference